Hi, and welcome to this part 3 of our V-block project. Today we're going to be looking at the side grooves, and we're going to be starting by laying them out, and then we're going to go and mill them. But we're going to be milling them in 3 different ways. So that's pretty well what we'll be doing today as far as machining goes. But before we get into that, I received several good or great questions in the comments of our last video, the part 2. And I think I'll take a few minutes now to answer some of those questions. The first question is, well, wouldn't it be faster to use the mill to square up the blocks that we squared up in the last video? And the answer is yes, definitely. But that is not the reason why I'm using it. There is 2 reasons actually. I'm using it because a lot of people asked me to use the shaper because they wanted to see it go. They've seen the shaper in my videos in the background, and I've never used it on camera yet. So that's the big reason. The next reason that I would want to use the shaper is the tooling cost. Now, in a home shop, tool cost is the main expense. So if you want to be able to cut a lot of material for little or no money, well, the shaper is the way to go. And that's why I have one in my shop, especially when I'm cutting rough and difficult to cut materials like cast irons and bronzes. So that is why I use it generally. But we should maybe take a little bit of a historical look at why the shapers exist, because that naturally is the next question that one should ask. And they exist because they're dinosaurs, really. They predate milling machines, and definitely the vertical ones, and a little bit the horizontal ones. And they were used mainly to square up material and to machine things such as grooves, but at a time where bearings just weren't available. Now, what's the nice thing with a shaper is you can work accurately with a machine that doesn't need any ball, roller, or pin bearings. And that is really nice. So that is why they used to exist. It's just a question of technology that was available. And way back when, bearings just weren't available. Sorry, ball bearings, that is. And as we progressed through time and ball bearings became, and roller bearings became more and more available and cheaper, well, slowly the milling machines took over for the shapers. And today, well, they don't even produce shapers anymore that I know of. I haven't seen a new shaper or shapers sold new in catalogs for years and years and years. But there are a lot of them out there, and they can be picked up for relatively small amounts of money, and they really work accurately compared to a cheap milling machine. So that is historically why they exist. It's just that they've always been around, and there's really no need for them now because they're so much less productive than other machines. I mean, in an industrial setting, you just wouldn't make money using them anymore. But there's other specific reasons for wanting one around, and that is for certain internal grooving jobs. Let's say you want to cut an internal keyway and don't have broaches available. Well, a shaper can do that kind of work because a shaper cuts linearly. It doesn't cut in a rotation, and that means that it can get into interior square corners. So if you wanted to machine a square hole, well, that is something that you can definitely do with a shaper, and that is something that you cannot do with a milling machine. And there's all kinds of examples like that. Internal keyway slots, internal gears, etc., etc. So that is another reason why you might want to have one around. Next question, well, we'll head over to the machine for that because it has to do with the direction of ram versus the direction of feed. So let's head over to the machine and take a look at that. The next question, the second question, has to do with something that I forgot to mention in the first video, so thank you very much for the question. and it is that, does your machine always feed on the return stroke? Now, these machines cut, and this is a forward cut that I was doing here, so as the ram comes out, I'm cutting, but the machine actually only feeds on the return stroke in the setup that I was using. And that is normal because I don't want to feed the machine sideways as my cutter is cutting. I want it on the return stroke, and that's one of the reasons that we have a little clap in here. Well, that is fine and dandy, but this person noticed that I was changing the direction of feed. I was feeding in one direction and coming back in the other because I'd sharpened my tool to be able to cut in both directions. Well, he was right. I have to adjust the machine to always maintain that feed on the return stroke. So what I have to adjust, well, is right down here. So it's a little tight. We'll bring the camera over, get in close, and see if we can get a shot. So here's the problem. I have over here a directional feed. I can go in one direction or the other. And I have here something that adjusts the amount of feed and the moment that the feed will occur. Do I want the feed to occur on the front stroke of the ram or on the return stroke? Now right now I'm in the middle of this semicircular groove, and that means that there is no feed set on the machine. So I can engage the feed all I want, nothing's going to go anywhere. But should I loosen this, pop this out, and come over to one hole on one side of the 0 mark, well, I'll be feeding on in one direction, and I don't know which one it is here. It's not important, and we'll see why in a second. But let's say this is feeding the table on the return stroke of the ram. Now, that's fine. Let's say I went to the other side of the eccentric over here, something like that. That would be the opposite. So right now I would be feeding on my forward stroke. So if I change from one side to the other here of the 0 mark, I'm going to be changing the moment at which the feed occurs. Now, if I'm cutting on the forward stroke and I've adjusted my moment of feed to feed on the return stroke when my table is going in that direction, well, that changes when I change the direction of the table. If I just change the direction of the table and don't adjust the moment of feed, well, it's going to feed on the forward stroke, and I don't want that. So what I omitted to mention was that when I change the direction of feed, I also have to change the moment of feed. Now that would seem like a lot of work, but actually it's a lot less work for me, thanks to old arthritis, than cranking this crank around 20 times to get back to my start point. So that is something that's important to understand. You want the table to move sideways when you're on your return stroke, when you're cutting in a forward stroke fashion. Real important to know, and thanks for that great question. Now, the next question has to do with ram droop. That's not something that happens like what happens to men in their mid-50s. That's not that kind of droop. No, this is loose in the ram, in other words. As the ram comes out, well, the tool tends to lower very slightly. And that is normal. I mean, if this ram moves, it's because it's loose in its bearing surfaces. If it were tight and had no play, it wouldn't be able to move. So you have to accept that. These machines aren't the most accurate. Now, a brand new top-of-the-line machine has very little play in it, I can agree. But as they get old, well, that droop or looseness increases. And I wouldn't get upset about it. Really, on this machine, and this is a really nice one, it cuts quite accurately. I can work to about 1/1000 of an inch without any problem. But on some, well, it's a little less, but that's okay. This isn't a surface grinder, it's a shaper. So you have to expect that it's not going to be that accurate. If you're getting a couple of thousandths within what you expected, well, you're doing pretty good here. Now, one thing you can do, or two things you can do to correct for the droop, well, would be to adjust your gibs if they're adjustable. Mine are, but not all the machines have adjustable gibs. Or work as closely to the column as possible. And don't put the parts out towards the end of your table, because that makes the ram come out even further and amplifies that movement due to looseness. So, thanks for another great question. Now, the next question, we'll head back to the bench because honestly, I got a sore foot and I'm a little tired of standing up. So see you in a few seconds. The next question has to do with feeds and speeds, and there's a difficulty here. We're used to calculating speeds, cutting speeds, not cutting speeds, but rotational speeds, starting with the cutting speed of a specific material, let's say 50, 60, 70 feet per minute, and then just using a formula to put that into rotation to get our RPM. Well, that doesn't work on the shaper, obviously, because it cuts in a linear fashion. And that makes it simple in one way and complex in another. Simple because if you have a material like what we're cutting here that has a cutting speed of 70 feet per minute, well, you would like your tool to travel during its cutting at 70 feet per minute. Well, how do you calculate that? You're going to have to estimate the length of the stroke that it's cutting on, and then work back from there to the number of strokes per minute you're using, and just do a cross multiplication to figure out how many feet per minute you're actually getting. So that's not too complicated, but it is a little, because there's not a speed you can set the machine to. You set the machine to a stroke per minute, but then the length of the stroke that you're using alters the speed that the tool is moving at. You have to remember also that on the stroke, it's cutting only half of the time, so you have to factor that into your calculations. The feed, however, is quite straightforward. And when we calculate the feed on the mill, let's say, well, we have to multiply the required RPM for the material we're cutting by the number of teeth, by the chip load that we want to use. Now, we've seen all this in our chip speeds and feeds videos, so just go back and take a look if you're not sure. So that's how we used to calculate the feed on the mill. But really, on the shaper, all we need is a chip load. So if you want to rough a part out, depending on how powerful your machine is, well, you could use something from 5 to 7, maybe 8 thousandths of an inch. On my machine, it's not very powerful, so I have to be quite conservative. And for finishing, 2 or 3 thou per inch with an appropriately sharpened tool. But there's no calculations here. It's a distance per stroke, and you just have to look at your machine, what your different settings are. You're going to have, like in my case, 3 possible settings: a finishing, a medium, and a roughing setting on your machine. So, relatively simple for feeds. Now, the final question had to do with something I just said off the top of my head in the last video, and that was that you shouldn't be using circuit breakers as safety switches. The question is why? Well, one is, and electricians out there, please sound in on this, I don't think that breakers should really be used to be turned on and off regularly. I mean, if you're going to be turning something on like 3 or 4 or 5 times an hour during a job or more, well, it better be a switch that was conceived to do that. The second thing for me really is a practical one, and it's something that you just don't want to get used to doing, because in certain situations it is dangerous. Now, obviously in an industrial setting you need lockout switches, but at home you won't have that. You don't have a switch you can actually physically put a lock on and say, I can work on this machine safely, no one can turn it on. You can't lock out circuit breakers. I mean, you can lock out a whole panel, but you can't lock out a circuit breaker. And often in larger shops, or sometimes in home shops when the shop is in the house or in the garage, well, the electrical panel is not necessarily in the same room that your machine is in. So you would physically have to head over and turn it off and then come back. There's a problem with that, and that is that seeing as you're not close to your switch, someone else in the house may want to turn that breaker back on, thinking that it was activated by an overload somewhere, and let's just go turn it back on. And that could really cause a problem for the person working on the machine. So that's the reason why I would say really it's not a good habit to get into. And that is the location of the switch that is the problem. But electricians out there, as I say, sound in. So that's the questions that I wanted to answer for now. Let's get our surface plate cleaned up and let's start laying out those lines. Let's start by applying a thin coat of layout glue on the 4 surfaces that we're going to groove. Now, if we take a look at our print here, we can see that the groove is 400 thou from the base of the part, and that the groove's height is 1 inch 400 thou minus 400 thou, so the height is 1 inch. And I can see that its width is 350 thousandths of an inch. Now, that is the dimension of the groove once the part is done. But this groove isn't going to be ground, but the outside of this part will be ground, and that's why I left material on those external surfaces. So my block doesn't measure the 1.7 as we see on the print. It actually measures 1.728. And that means that the 0.4 dimension for the first line I want to lay out here, well, isn't going to be 0.4. It's going to be 0.414, 14 thou more, because I have 28 thou total, 14 on the bottom, 14 on the top. So I'll lay out my first line at 414 thou. Now, here's something that needs to be said. This is my good old Starrett number 454 height gauge. And on these old gauges, well, the scribing tip won't go all the way down. Actually, the scale here starts at 1 inch, because that's about as low as this will go. But I want to scribe a line at 414 thou. How am I going to do that? Well, pretty simple. I'm just going to use this accurate 1, 2, 3 block to raise my part by 1 inch. And that way I can set my height gauge to 1 inch, 414 thou, and scribe my first line on both sides of the block. Now, I'll be scribing the same lines on the smaller block, but the smaller block is smaller in every dimension. We haven't left very much on there for finishing. We've only left about 4 thousandths of an inch. So that means that I'll be laying out the lines on that smaller block really to 1 inch 402 thou, okay, or 402 thou for the first line, plus the 1 inch of the V block. But this V block here isn't a hindrance, it's actually a blessing, because we saw that that groove, its height is going to end up being 1 inch. So all I have to do, and this is going to save me a lot of work, is set up my height gauge for each block, scribe the bottom line, and then remove the 1 inch height gauge and just scribe the second. My block will have lowered by precisely 1 inch, so I won't have to set up for that second line. So now all that's left to do is to lay out the width of the groove, which is, as we can see on the front view of the drawing, 350 thousandths of an inch. And for that, well, I'm going to set up to 1 inch, 350 thou, set my block on my 1 inch spacer block, or my 1, 2, 3 block, and scribe a line. But what about the over dimension? Well, in this dimension, my block measures 2 inches. I couldn't leave anything on there because I started with a block that was already 2 inches, and that is going to have to be taken into account a little later on. But for now, just laying out this line, I'm going to lay it out to the dimensions on the print because my 2 inch dimension is 2 inches. There, my grooves are laid out. Let's head on over to the milling machine. Now, these grooves have a width, a height, and a depth. And for that, well, I'm going to need a really well-aligned vise. So, first operation, align your vise parallel with the longitudinal axis of the machine, or if you prefer, the table's axis. There, that's pretty good. If you want to learn more about tramming a vise or aligning a vise, well, we have a video on that. So here's the title. You can find it on my webpage, THATLAZYMACHINIST.com, or through a YouTube search or through a Google search, whatever you feel like. We're going to get back to setting up our part, and what we need to do now is to set up our part in the vise on parallels. I want the 414 thou side on my side here. Okay, my part is set up, my vise is aligned, and I have my 3/4 inch end mill in the machine here. So I'm ready to start cutting. But I mentioned that we were going to do this in 3 different ways. And what are those 3 ways? Well, this block here is going to be done by coordinates. So I'm going to do both grooves by coordinates, and that'll be one way of doing it. The other block, the smaller block, will do one side without edge finding, and we're going to get it accurate by measurement. So we're going to not go by numbers, we're just going to measure, cut, measure, cut. And the other side of the small block, well, we're just going to cut by eye to those laid out lines. And then, well, we'll be able to compare what the advantage is of doing one over the other. So, they all start, however, with the same operation. That is roughing out. I have a fair amount of material to come off here. Now, if I were doing it on a horizontal mill with a side and face cutter, well, I could hog that out in 2 passes just to get the proper width. But in this case, I'm going to have to remove several passes. So I'm going to cut, come back, move over, cut, come back, move over, and so on and so forth till I work my way down. Now, I have laid out lines on this part, and I'm going to gauge myself on those lines. So I will come close to them, but not touch them. They are my final dimensions. So I just want to leave some material on there for finishing by numbers. So let's go get our safety glasses on, that's very important, and we can start roughing this part out. Now when I'm done roughing that first slot, I'm going to flip the block over, keeping the bottom of the block on this side of the machine. Very important not to flip in the other side. Why? Other direction. Why? Because that groove isn't in the center of the part height-wise. And if you flip it in the other direction, well, you're going to be way off. So we'll just flip the block and rough the other side out, and that way we can do the finishing on both sides with just one setup. So let's go get our glasses and start roughing out. There, you can see that I've left just a little bit on in each direction, and that will be enough for finishing by coordinates. Okay, so that first groove on the large block is completed. Well, no, it's roughed out. Now what I want to do, because there's a time to rough things out and there's a time to finish things, and you don't want to get them confused, well, I'm going to rough out the other side of this block at the same time, the second groove. And seeing as I'm in a roughing out kind of mood, well, I'm going to rough out the two grooves on the small block as well, and all my roughing will be complete. And then, and only then, I'll move on to finishing those grooves to size. And since I like to project what's coming up, well, I know that by the time I finish roughing, the last groove that'll be in there would be a small groove on one of the side grooves on the small part, and that will be the groove that I've decided to finish strictly by eye. So our part will already be set up, and we'll just finish that one by eye, then flip it over, finish the other side by measurement, and then come back to this first block and finish these grooves by coordinates. So you don't have to see all this roughing, it's just more of the same. So we'll come back to the finishing on one of the grooves of the small block. So I'll see you in a few seconds. Okay, so all the slots are roughed out. That was the second slot roughed out on the small block, so it's the last one I had to do. But this is the one that I want to finish by eye, so I'm not going to pull the block from there. I'm just going to get my brush and brush it out quickly so that I can see my lines, and I'm going to finish it to those lines. But there is a method here. I'm going to get my height or depth first and come right down the middle of the groove, then return back without cutting, just on the zero, okay, where I've cut just previously, and then take a cut on this side of the block here, because I'm going to come up to my line and skim the edge. I won't have to cut too much on the bottom, and that'll reduce tool deflection. But also, it will permit me to cut this side of the groove in a conventional milling fashion. I don't want to climb mill here, and that means that when I get through the part here, I'm going to go over to the other side and cut it with the part going back to its origin, and that means that I'll be conventional on that side as well. Well, what is conventional milling and why is it important? Well, there's two basic ways of milling.
One is conventional and one is climb. So conventional milling and climb milling. And here they are. In this case, I have a tool rotating clockwise and a part that is feeding against the rotation of the tool. So as the part feeds into the tool is pushing back on the part. This is conventional milling. In this example, I have a right or a clockwise turning tool, but I have a part that is feeding in the same direction as the rotating tool. So in this case, the tool wants to grab the part or climb onto it. And this is obviously climb milling. Why is this important? Well, conventional milling does not give that good a surface because it forms a chip from the small end up to the large end. And that means that it has difficulty forming the chip in the beginning. If you remember our 4 phases of chip formation that we saw in the chip speeds and feeds video, well, we had a penetration, compression, flow, and separation. I had a hard time there. This one has a hard time getting to the compression stage because it's starting up with nothing, no thickness. So it's rubbing at the start. I get burnishing. And that tends to lessen the finish. And it also increases the cutting pressure. So this isn't as an efficient way of cutting as climb milling is. Now climb milling, the chip starts thick and comes down to thin. So I have no difficulty starting my chip up here. And seeing as it's cutting well from the start right through to the end, well, I get no burnishing. So my finish here is much better and it is a lot more efficient. Really, this climb milling is somewhere around 20% more efficient. So now we can see that, but why am I insisting on conventional milling here for cutting the sides of that groove? Well, I'm insisting on that because even though this is a more efficient and I get a better finish with this method, climb milling, this method, conventional milling, is far, far safer. This conventional, I have a tool pushing against the part feeding into it. So all the backlash is on this side. There's nothing that can lurch forward. Here I have a part feeding in the same direction as the tool rotation wants to pull on. And that means that my backlash is on this side, and this part could lurch forward by whatever amount of looseness I have in the lead screw of my milling machine. So, much more efficient and better finish, climb milling. Much less efficient and lesser finish, conventional milling. But conventional milling, especially in a home shop, because our machines aren't equipped with backlash eliminators, well, conventional milling is the way to go. It's the safe way to go in the home shop. So, let's get to it. So that slot is complete, and we did it by eye. We still have one to do on the other side of this part, and we're going to be doing that one by measurement. And then we have 2 slots to complete on the larger block, and we're going to be doing those by coordinates. And that's what we're going to be doing in our next video. Well, that and some hole drilling and some tapping. So until then, have fun. Be safe. It's so important. And happy machining.
Ok, il a ses...